1990 and named in memory of Paul Klopsteg. He's an American physicist, one of the founders of AAPT, and AAPT president from 1953 to 1954. The Klopsteg Memorial Lecture Award recognizes outstanding communication of the excitement of contemporary physics to the general public. I invite James Hansen, please, to join me on the podium. This summer, the Klopsteg Award is presented to James Hansen, who works at the NASA Goddard Institute for Space Studies in New York City. Dr. Hansen is recognized for his skill in communicating his work on global climate change to the general public. As you can read in the citation in the on-site guide, Dr. Hansen has made substantial contributions to our understanding of global climate change and has also played roles in influencing legislation in the U.S. Congress and in significantly communicating awareness of the threats of climate change to the general public. I'm pleased and honored to present to you, James Hansen, the 2011 Klopsteg Memorial Lecture Award. The full award consists of a plaque or a citation, a certificate, and a check. That lecture is titled Halting Human-Made Climate Change, the Case for Young People and Nature.
Thank you. Is this working? Can you hear me? No. No, it's not working. So you have to turn this one off?
Closer.
Okay, is it working now? Okay, how about now?
Yeah.
Okay, great. Yeah. Thank you. The case for young people and nature. The situation is that if we do not take steps to stabilize climate, it will be a case of intergenerational injustice. That is not what I push. Try this. Okay. Okay, moving on. And yet, the status is that there continues to be a big gap between what is understood about global warming and what is known about global warming. Understood by the relevant scientific community and what is known by the people who need to know, and that's the public. I used to say the public and policymakers, but what I've learned in the last several years is a lot of policymakers actually understand the situation, but they're simply they don't have enough gumption to take the actions that are needed to deal with it. Because the truth is, we have a planetary crisis, and yet the public is not aware of that. The reason that we can have this situation of having an emergency, and yet it's not obvious, is because of the inertia of the climate system. The ocean is 4 kilometers deep, the ice sheets are 2 or 3 kilometers thick, and they don't respond quickly to forcings that we apply to them. But that inertia is not our friend on the long run, because once they do start to respond, you can get to a situation where you pass tipping points in which the dynamics of the system begins to take over, and it's too late to change the forcing. For example, if an ice sheet begins to disintegrate and slide down the slope into the ocean, well, you can reduce the greenhouse gases then, but you're not going to stop the ice sheet from disintegrating. So that's an example of a tipping point. And that's an irreversible process on any time scale that we can imagine. It takes thousands of years for an ice sheet to grow by snowfall piling up. And similarly, another irreversible process is extermination of species. And humans are putting pressure on different species in a number of different ways. I remember when I was a 9-year-old boy and started to deliver the Omaha World Herald, at the bottom of the page, at the bottom of the front page, they would have this tally on the number of whooping cranes that had arrived in the wildlife refuge in Texas. The number of whooping cranes had decreased to 15 in the early 1940s, mainly because people were shooting them and the habitat was being reduced. But when they made laws to make it a crime, it does seem that we may have saved that species. They got into the 20s and then the 30s, and now there are a few hundred whooping cranes. And but there's still, until recently, there was still just this one flyway that ended in Texas. So they're trying, but that's a little dangerous to have just one nesting ground for them. So they're trying to establish another one in the eastern United States. And so they have this little light plane which is training some of the whooping cranes to follow migration paths to end, I think, in Florida. Well, that's one species, and maybe we can save that species, but there are millions of species. And, well, here's another one. This is the armadillo. This guy has been around for more than 50 million years. Compare that to how long humans have been on this planet. He's a survivor, and he's, I think, not going to have any trouble with global warming. But I got an email from a man in Arkansas who said every year these armadillos were moving several miles north. I guess he was seeing them as roadkill on the highway that he drives all the time. And that's not surprising, because for the last several decades, the average temperature, if you average the temperature over a decade, so you remove a lot of the variability, then what you see is that a given temperature line is moving forward at a rate of about 35 to 40 miles per decade. So 3 or 4 miles per year on the average. And some species, like this one, can migrate that fast, but others can't migrate that fast. And this rate of climate change, rate of warming, is unprecedented as far as we know in the Earth's history. And once that total movement of the climate zones becomes substantial relative to the size of the zone in which a species can survive, you can drive a species to extinction. They don't have air conditioners to change to the climate that they can survive in. And we know that in the Earth's history there have been global warmings of several degrees Celsius, which drove to extinction a substantial fraction of the species on the planet. And then over hundreds of thousands and millions of years, new species evolved. But again, that's a time scale which we can't imagine. On any time scale that humans can imagine, it would be a much more desolate planet if we drive a substantial fraction to extinction. And the IPCC, Intergovernmental Panel on Climate Change, estimates that if we stay on business as usual, we will commit 20 to 40% of the species on the planet to extinction by the end of the century, if we stay on business as usual. It is a matter, therefore, of intergenerational justice. And when I first showed this photo of my first grandchild, because when I gave a talk at the Omaha Observatory, because the day before I had been, a newspaper article called me the grandfather of global warming, which is not correct. There were many people talking about global warming 100 years ago. Not many people, there were some scientists. But I was really a grandfather. But that was just sort of a joke. It wasn't until I had testified to Congress in the 1980s, and then I decided I didn't want to be involved in the public aspect of this problem prefer to do science. And so for 15 years, I declined invitations to do television interviews and refer them to Steve Schneider and Michael Oppenheimer, people who like to do that and who do it very well. But finally, in the middle of the Bush administration, when it became clear that nothing was being done about this, I decided to give some public talks, and I used my grandchildren to help me explain the problem. The physics is very simple. When you add CO2 and other infrared absorbing gases to the atmosphere, you make the atmosphere more opaque in the infrared part of the spectrum. So therefore, the radiation to space will arise from a higher level in the atmosphere. And because the temperature falls off with height, that means the radiation to space is reduced. And the planet is temporarily out of energy balance. There's more energy coming in than there is being radiated to space. And that total imbalance due to the greenhouse gases and the other things that humans are doing, including air pollution, the particles in the atmosphere, is a forcing someplace between 1 and 2 watts. And Sophie was trying to explain that it's about 2 watts, but Connor could only count 1 watt. And now, finally, we can answer what the remaining imbalance is. The planet has warmed up by 0.8 of a degree Celsius, so that's, it's trying to reestablish equilibrium. So it's warming up, but it's still out of balance by some amount, which we would like to know. Well, most of that energy has to be going into the ocean because the atmosphere has very little deep capacity and the conductivity of the continents is very low. So now, with these Arco floats that began to be distributed around the global ocean about 3,000 of them, they have an instrument package that yo-yos down to a depth of 2 kilometers and yo-yos back up and measures the temperature very accurately. But we can see that over the last several years, the planet has been out of balance by, averaged over the planet is probably about 0.6 of a watt in the last 6 years, from 2005 through 2010. When the floats had their most complete global distribution. What's measured is an imbalance of about 0.6 of a watt per meter squared. That period is during the solar minimum. And I suspect that the imbalance averaged over the solar cycle is probably about 3/4 of a watt. That means that we've only experienced about half of the warming due to the gases that are already in the atmosphere. The rest is in the pipeline. And so what we see is that the temperature fluctuates from year to year, but if you average it over 5 years to get rid of the El Nino cycle, or 11 years to get rid of the solar cycle, then you see that over the last few decades it's almost a linear increase in temperature. And averaged over a year, last year, most of the places on the planet are warmer than they were in the period of climatology, which was 1951 to 1980. But over just a season, last winter, December, January, February, you can see there are many places on the planet which were actually cooler than they were 1951 to 1980. It was a La Nina year, so the tropical Pacific was very cool. And both the United States and Europe had an unusually cool winter. That's because the interannual variation of a seasonal mean temperature is larger than this global warming of less than 1 degree Celsius. But if you're perceptive, you will notice that the frequency in which you get seasons that in the period 1951 to 1980 were called unusually warm seasons. They occurred 30% of the time. Well, they're now occurring more like 60% of the time. And more, if you want to recognize the change the frequency of extreme warmth you can see more easily in the summer than in the winter, because the unforced variability in the winter is much larger than it is in the summer. And if you want to find what was a 2 standard deviation anomaly in the 1951 to 1980 period, that's the color, this dark red or brown color, is more than 2 standard deviations above the normal. Well, this is the last 4 years, and the area which would have been 2.5% on the average, 1951 to 1980, was 28%, and 21%, and 30%, and 39%. So a 2 standard deviation warm anomaly will be noticed. I think 2011 in Texas is clearly a 2 standard deviation, at least, anomaly. I'm not sure what it will turn out to be in Omaha, but I suspect it might be under one of these brown areas. But the chances are now much greater than 2% that you're going to get such a strong anomaly. Now, the basis of our understanding often said, oh, it's all based on climate models. That's not true. In fact, the primary basis of understanding is the Earth's history, how the Earth responded to changes in the boundary conditions, changes in atmospheric composition and surface properties in the past. And also, now we have global satellite observations of how the Earth is responding to the rapid increases in greenhouse gases in the last few decades. And the climate models, in theory, are also useful, especially for projecting into the future. But let me give you one example from the Earth's history. This is the last 65 million years, and it's the temperature in the deep ocean, which in the first half of this period, up to about 34 million years ago, the planet was so warm that there were no large ice sheets on the planet. The sea level was about 60, 70 meters higher than it is now, until it had cooled off to a point where ice began to form on Antarctica, and that continent glaciated, and the planet got a couple of degree or two colder. We know this is an interesting period to look at, because we know that the principal drive for climate change on this long time scale had to be the amount of carbon dioxide in the atmosphere. Because at the warmest times, there was about 1,000 parts per million of CO2 in the atmosphere. And at the coldest times, there was only as little as 170 ppm. That's a change, that's a kind of forcing of more than 10 watts per meter squared. The other things, the amount of energy coming in, well, the sun is slowly getting brighter over this time period by about 0.4%, but that's only 1 watt per meter squared, because the Earth absorbs 240 watts per meter squared of energy from the sun. And the changes at the surface were also not very large, because the continents were already, 65 million years ago, they were already close to their present latitudes. Except for India, which was still south of the equator, and it was moving north at a rapid rate of about 20 centimeters per year. And it was moving through this Tethys Ocean, now the Indian Ocean, which had long been the depot center for the major rivers of the world. The point is that the amount of CO2 in the atmosphere, when did I start? Okay, so I've used almost 20 minutes. Okay, so